is called a divergent sequence. This is known as a divergent sequence. So we have truth now. A sequence is either convergent or it is divergent. We don't have any other behavior. So let's try to give an example of a sequence which is convergent, and then we will give another example which is a divergent sequence. Then we will move on to other things where we will talk about this limit of a sequence, little bit more about limit of a sequence, and then about the relation between the boundedness of a sequence and its convergence. So first let us, I will consider a simple example. The simplest example I will consider that let xn be, every term is b, be a constant sequence, be a constant sequence. Then this sequence, constant sequence xn converges to the term which is constantly throughout this sequence. See, we will just use the definition. Let us take some epsilon to be a positive number. Then what we require, then for any n in n, let us look at this distance xn minus b. What is this thing? This thing is xn is b because each term of the sequence is equal to b minus b, and it is equal to 0. Hence, what I can say now that hence, and this 0 is clearly less than epsilon because you're choosing epsilon to be a positive number. Hence, for any n greater than or equal to k, but here is k, you are going to get this k to be equal to 1 because we don't need to go drop any terms here. Indeed, for every term, the distance of this every term of the sequence from point p is equal to 0, which is strictly smaller than epsilon. Hence, for any n bigger than or equal to 1, what we have this xn minus p less than epsilon. And this epsilon was an arbitrary number, a positive number. So this is true for every epsilon, and hence by the definition of a convergence of a limit, it follows that this sequence is a convergent sequence, and its limit is b. So one thing is true for generally, that a constant sequence is always a convergent sequence. Okay, now let's look at the sequence which is divergent. To establish that a sequence is divergent, you just need to find a one particular choice of epsilon for which the terms of the sequence after any stage doesn't become smaller than that particular epsilon. As you may see this demonstration here also, if we consider this sequence, consider this sequence minus 1 power n, and let us write this to xn. Then I'm going to claim that this sequence is not convergent, but that this sequence is not convergent, and but for the time being, suppose this sequence is convergent. Suppose that it is convergent. It is convergent, and whenever it is a convergent, it must have a limit convergent, and say this sequence converges to some number x. And then according to the definition of convergent sequences, what convergent sequence says that for every, just a minute, So what it says that for every positive number, but we will choose some particular positive number for every epsilon, and I will restrict epsilon now to between a positive number which lies between 0 and 1, which is strictly less than 1. And by the definition of convergence, I will be able to find a positive number greater than 0, obviously positive, so it's greater than 0, it's a natural number, such that the distance of the terms after k from x is less than epsilon. And this is true for every n greater than or equal to k. So this inequality is true for particular choice of k also, and the particular choice I'm going to take k and k plus 1, and that is xk minus x is also less than epsilon, and k plus 1th term and minus x, its modulus is also going to be less than epsilon. Okay, now let's look at this thing. What is the distance of kth term and k plus 1th term? First, look at what is this given sequence. We have this given sequence here, and the first term is minus 1, then next term is 1, and then again you have minus 1, and continuing so. That means uh, uh, these are the alternating terms. First you have minus, then you have plus, minus, plus, minus, plus. So if you look at any two consecutive terms, if the first term is positive, the second has to be negative. If the first is negative, the second has to be positive. So if first is 1, the second has to be minus 1. So if kth term is, you have two possibilities. If kth term is 1, then clearly this k plus 1th term is always going to be minus 1, and then you will have this distance to be 2. And in the other possibility, when you have this kth term to be minus 1, then its next consecutive term has to be 1, and then you will have this modulus to be again modulus of minus 2, and minus 2 is nothing but minus 2 is again 2. So whatever situation you take, this distance is always going to be equal to 2. Okay. Now, but at the same time, I'm going to bring in the triangle inequality, and you will also see the power of the triangle inequality here. You will see other in the coming two results also. And what this triangle inequality I'm going to use, how I'm going to add and subtract the number x to which I have assumed that the sequence is convergent. And then I will, by triangle inequality, I have this less than or equal to xk minus x plus x minus, if we have minus here, sorry, plus, and it is minus sign here, be careful. So I have x minus xk plus 1. As seen, the distance of both these terms, kth and k plus 1 term, from x is less than epsilon, so you would have this to be less than twice epsilon. So what you get here? You get here 2 and 2 cancelling from both sides. This is a non-zero term. I will get 1 strictly greater than epsilon, and clearly this is contrary to this assumption that your epsilon lies between 0 and 1. You get this as a contradiction. Hence, the assumption that the sequence is convergent is not true. This implies that this is a divergent sequence. Now let's look at this sequence closely. Note that this sequence minus 1 to power n is a bounded sequence. It has only two terms, two distinct, its range contains only two terms, either it is 1 or it is minus 1. So it's a bounded sequence, its range is a finite set, it is a bounded, but it is not convergent. But not convergent. So one way it is clear that a bounded sequence need not be convergent, but the other way, this phenomenon is quite good, and the other way expectation is that a convergent sequence is always bounded. Convergent sequence is bounded, but whereas a bounded sequence may not be convergent, as seen from the previous example. Let's do a quick proof. Uh, Suppose you have this sequence which is convergent, and suppose it is convergent sequence. I'm executing CGT to convergent, and say its limit is be x. What it means then, for every choice of epsilon, and in particular I will take some particular epsilon, I will take epsilon to be 1. There exists some number k greater than 0 such that we have this number xk minus x, xn minus x less than epsilon for every n greater than or equal to this number k, and epsilon I'm taking here 1, y2, keep epsilon something different. This is definition of convergent sequence, and now again let's take the help of the this triangle inequality, and I will consider this modulus of xn, and inside it I am going to mm, subtract my x and again add back to it so that it remains same, and then apply the triangle inequality. It is less than equal to xn minus x plus x. So if I choose n to be a number which is greater than or equal to k, then I will have this distance of nth term of sequence from x is less than 1 plus mod of x, and this is true for every n greater than or equal to k. Let this number be some m prime. 1 plus mod x. This is a fixed number, it doesn't change with n. And provided but this validity of modulus of xn less than m prime holds only for those n which are greater than equal to k. Now let us now what about all the terms which are before this kth term, that is x1, x2, so on. And since there are finitely many terms, let we can choose a number m which is maximum of the modulus of these terms, mod x1, mod x2, so on up to mod xk minus 1, and also of this m prime. Now you can see clearly that modulus of each term, irrespective whether it is greater than or equal to k or not, is less than or equal to m for every n greater than or equal to m. So this implies clearly that this shows that this sequence is a convergent sequence, bounded sequence. It shows that this sequence xn is bounded, as the modulus of each term is bounded by this number and is bounded sequence. So this establishes the relation between a bounded and a convergent sequence. And finally, and another thing that we need to observe is that we said that a sequence xn is converging to some x, but we haven't told you yet that is it true that this sequence converges to only x, or is it possible that it converges to some other y also? And we will establish that okay, there is no such situation where you have a sequence which converges to two different numbers, and this is known as uniqueness of the limits. That means the sequence, if it converges a unique limit. A sequence xn can have at most one limit. Either it will have no limit, in that case the sequence is divergent, but if it is if it is convergent, then it will have a one limit only. Suppose that if it is not convergent, then there is nothing to prove, it will have no limit. And on the contrary, on the second possibility, suppose that this sequence is convergent, and at the same time, let us suppose that this sequence converges to 2 points, one is x and another is y. Now, then for any epsilon greater than 0, using the definition of the convergence, there exists numbers k naught and k1 because the sequence converges to x and y. So when it converges to x, I can find a number k naught for which x, the distance of the terms of the sequence from x becomes less than epsilon by 2 for every n greater than or equal to k naught, and when it converges to y, then the distance of the terms after certain stage from y becomes less than from epsilon half for every n greater than or equal to k1. And note that if you choose n to be a number which is greater than or equal to the maximum of the k naught and k1, then both these inequalities star and double star hold for that particular choice of n. So uh, clearly the both inequalities star, double star and star are true for any number n which is greater than or equal to the maximum of the numbers k naught and k1. So our job is to show that the sequence has a unique limit, to means to show that x is equal to y, and the better way is to show that the mod distance between these 2 points is 0. That will be enough to establish that the points are same. How we are going to do? I'm going to use again the strength of the triangle inequality. I'm just inserting a term and taking out it at the same time, and then I can apply the triangle inequality. I will have x minus xn plus xn minus y. And now if we choose n to be a number which is greater than or equal to maximum of the numbers k naught and k1, then as said above, I will have these numbers distance x, nth term of sequence from x will be less than epsilon half, and the distance of the same term from y will be less than epsilon half. Hence, I will have this x minus y less than epsilon half. Adding it to epsilon half, it will be epsilon. And what you get finally, you get that this distance, which is a constant number, x minus y modulus, is less than epsilon. And you see that since epsilon is arbitrary, so what you have, we have that this number x minus y is less than epsilon for every positive number. And at the same time, you see that this is a non-negative number. This modulus is a non-negative number. Now you have a situation where you have a non-negative number which is strictly smaller than every positive real number. And then what that number can be? That number can be only the 0. We cannot have any other non-zero number which is non-negative at the same time and less than from every positive real number. So such a number is only 0 number. So it gives you x mod of x minus y equal to 0. That is equivalent to say that the distance of x from y is 0 only when x is equal to 0. So, and hence it establishes the uniqueness of the limits of a